Okay, so logarithms. We're venturing into I'm gonna say a fun section. There's so many applications to this that I'm not even gonna talk about. Let's just get through it. Here's a scenario. Okay, I'm gonna give you a scenario based on exponential functions, just like yesterday, and then from there, I'm going to show you why or how. I'm going to show you why we may need to do what we're going to do, in hopes that you will sort of get it. Know that there is no real mathematical algebra when it comes to the inverse of exponential functions. I have to introduce something completely different and get you to adopt it and take it as one of your own. And that is this thing called logarithms. Okay. There is a relationship, but it's not just like, what you do to one side, you do to the other. Something that you're going to have to pick up. So here we go. Suppose you made an investment of some money known to double in value every year, which is probably not true unless you are going to forget it. Okay, time has an exponential effect on your money. Let me say that one more time. Time has an exponential effect on your money. Something causes something else to change. So what is your independent variable? What, Adam? Time. And that has an effect on your money. So the dependent variable, money. Okay. But here's the thing. And so in grade 11, when I start introducing inverse, I give you a scenario where we want to change the relationship order. So right now, time is X and money is Y. Is there ever a situation where we want to change that order and see, is there an effect of money on time? You see the difference? This is more science. Does anyone know what I'm talking about? Okay, you guys are looking at me like I'm crazy. All right, everyone, this might be a little longer, but I want to do this. Let's pretend, okay, that during the summer, temperatures fluctuate. It goes higher, it goes lower, blah, blah, blah. So the temperature could be like, it can go as high as like 40 degrees Celsius. And since this is the summer, let's pretend it goes only as low as 10 degrees Celsius. Okay, with me so far? And let's say I run like an ice cream truck business, and I found an amazing correlation. I found that if I sell $100 worth of ice cream, the earth will change its weather to hit about 20 degrees Celsius outside. And then if I push really hard on my sales and I earn $200 that day, miraculously, the sun is like, oh, really? You made more money? Oh, well, I'll up the temperature for you. Yeah. And then if I sell $300 in one day, the sun is like, whoa, you went really high. I'll go to 40 degrees Celsius for you. Is this a correct relationship? People are not shaking their heads. Why, Beta? The temperature or the sun is not dependent on how much money I make at all. In fact, what would you counter argue? Right, you might say it's switched. So data management people, you can say that this is a reverse cause effect. This is not a cause and effect. This would be a reverse cause effect. We need to switch these. You might also want to argue that this is a common cause effect. What is that? Well, if the weather is nice, the weather affects the temperature as well as the sales. So these may not necessarily be related, but I mean, it is related, but you know what I'm talking about. So clearly there are situations where I made a mistake. But sometimes it's not clear if I made a mistake. Let's say in science, let's say, um, Okay. If people took a survey, let's say there was a survey, and then say the number of burgers I eat is going to change my weight. What do you think? Right? The more number of McDonald's burgers I eat, the higher my weight goes. Sort of makes sense? I would agree. Would you also agree that it could be because of the reverse? All of a sudden, it's a little bit more ambiguous, isn't it? What if I say, you guys don't know Austin Powers, so I can't say that. Anyways, I think you get the point. There are situations, at least in science, where we want to see if there's a relationship by flipping the x and y axes, right? It's just a check. So this is what we're sort of going into with this example. Ian? Pardon? Yeah. So if you know, this is a long time ago. This is when I was like in high school, right? There was a series of things by there's a movie called Austin Powers. It's like 3 different movies. Terrible. Okay. It would not fly in this day and age. Back then, it was comedy. Right now, it would just be politically incorrect. Anyways, there's a guy. It's basically Mike Myers with a bodysuit, really, really big guy. And at one point in time, he starts breaking down and crying and just pouring his heart out. And he's sad that he's overweight. And the quote that he says is, I'm fat because I eat. And then I eat because I'm fat. Right. And it just keeps on going around and around and around. And I can't stop myself. And he starts crying, crying, crying. And then at the end of the day, he somehow loses weight. And anyway, it's supposed to be happy. It's supposed to be comedy. I don't know. Anyways, moving on. What if, such a tangent, sorry. What if you were interested in the relationship in opposite direction? You would then use, right now you're using time to calculate money, but right now, if you want to find the reverse, you would calculate the money, so you would use the money to calculate the time, AKA an inverse. Sometimes it's not easy to use the answer and guess the question. So that's why you learn to create an equation that is the inverse. That's what you learned last year. Okay. So the independent variable this time would be money, and your dependent would be time. So mathematically speaking, and this is hard, this is what's happening. Here's your answer, and you have some kind of base to an exponent, right? If you are given time, you can calculate the answer. But what if, like we said, you're interested in the reverse? What if it was, if you are given the answer, can you calculate the question? Now that is really hard in exponents. Try it. Think about it. What if you had 91, sorry, I just do 9. If you had 9 to the power of something obscure, 1.1. If you put that in the calculator, well, it's not as easy, right? 9 to the power of 1.1. That's 11.2. Now we can do that because we have the calculator. However, what if you have 9, right? Like, would it make sense for us to say 9 to the power of 11.2 equals 1.1? That wouldn't really make sense, right? There's, how do I go about it? So for logarithms, it's not as simple as just switching the order of the numbers and then doing some algebra to simplify it. Okay, there's nothing that we can do with a 9 and 1.1 to give you 11.2 other than this exponent here. What I'm trying to get at is, if we want to do an inverse of an exponent, we have to introduce a new system. And that is where we have logarithms. So if we have So from here, if, let's say, the base to the power of x gives me an answer, we can reverse it. We can reverse it by saying instead, we're going to do something called a logarithm of the exponent. Sorry, a logarithm of my answer. And you will get the original exponent. Now I know this is a little bit confusing. I should probably clarify. I'm writing my own thing here, and then you're probably going to get confused with this. Let me write it on this little spot here. Let's use, instead of x, y, and z, let's do this, okay? Let's pretend we have the answer is supposed to be from if we have b to the power of a. How do I reverse this? Well, if this was reversed and I want the actual exponent, what is the value of the exponent? To bring the a to the other side, instead of that, we would actually turn this into a log of that base using the answer. A short way of saying it is this. For the first initial question, something to the power of b to the power of a gives me the answer. Log b of the answer gives me the power. I'll say that one more time. B to the power of a gives me my final answer. So if I want to go in reverse, the log of the base of the answer gives me the exponent, gives me the power. Here's an example. Let's pretend the question was, what is 2 to the power of 3? Well, you know what the answer is. It's 8. In the same way, you can say log of base 2 of the final answer will give me the exponent. And that's a 3. You cannot. The calculator is pre-programmed to either use a base of 10 or a base of Euler's constant E. So I'm going to show you how we can deal with it. But for now, just so we get a hang of what logarithm is, we're always going to give you numbers that work nicely. We're going to just be using whole numbers for this section. Okay. Another way you could think about it is if you see an exponent, think of logarithms as the opposite of exponents. Okay. So once again, if y is equal to a base to the power of an exponent, log of the base of the answer will give you the exponent. Let's try this out. I'll give you like 30 seconds. Just take a look at what we did here. It's simply switching up some numbers in the location where you find them. 16 is equal to 2 to the power of 4. I don't think anyone's going to argue that. What if I did this? What's the exponent? Up to grade 11, you had to do guess and check, right? What's 2 to the power of 1? 2. 2 to the power of 2? 4. 2 to the power of 3? 8. 2 to the power of 4? 16. X equals 4. But now we can use a calculator. So what you're going to try to do is do this. Well, this can be rewritten as log of base 2 of the answer will give me my exponent, which is 4. Yes. Right now, the calculator is automatically using log 10. So right for now, you're just gonna have to get used to understanding what each number means. And then when I give you random questions to solve, it'll always be in terms of base 10. And if not, you will learn in 6.4 how to get around it. Next one, M is the answer, N is the base. How would you rewrite that? That? Yeah. Log base N of the answer equals a 4. Yes, even negative exponents work. Log of base 3, because 3 is the base, of my answer gives me my exponent. The opposite, so plus opposite is minus, multiplication, opposite is division. If you see an exponent, the only way to do the opposite of that, or find the inverse rather, is to do logarithms. Exponents are special. Okay. The back page is essentially all just extra practice, 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 and that's the end of our lesson. So here's what I'm going to ask you to do. I'm going to work with you to do A, and then do the summary. Okay. And the rest of class, let's just practice it. There are some homework questions you can try from the textbook as well, but we'll leave that alone for now. Log 3 of 81. You should be able to solve this. Log 3 of 81. If the base is a 3, my answer is 81. What was the exponent? If 81 is the answer and my base is a 3, what was the exponent? Yeah, 4. Good. Log 3 of 81 would be a 4. Ooh. In that same way, can you reverse calculate this and figure that out? Yep. Right now, yeah, you can't use a calculator, but it shows whether you understand what this is trying to say, right? This would mean I have a base of 2, and I don't know what the exponent is, but the answer was 1 over 8, which is 1 over 2 to the power of 3. So what's x? 2 to the power of what gives you 1 over 2 to the power of 3? Yeah, there you go. That's the exponent. Why is my base? Well, it is a 2, right? But 2 to the power of something is equal to 1 over 8, which I rewrote it as 1 over 2 to the power of something, because I wanted to give you a clue of what number we're dealing with. All right, same thing. If the base is 10, so here you can actually use a calculator if you want to. Try it out. Okay, log 10. So the log, notice how on my calculator by the shift, it's already 10 to the power of. That's the opposite of log. So log, which is automatically base 10, of 0.01, what do you predict the answer to be, right? If my base was a 10, what exponent gives me an answer 0.01, aka 1 over 100, aka 1 over 10 squared? What's x? Negative That's it. Yes, yes, this is something that you should have learned a while back, but because of COVID, I understand. Let's take a look. Here's my patterning, Yusuf. If you haven't seen this before and your teacher didn't do it for you, know that this is true now, okay? Sorry, everyone. I'm gonna do this for Yusuf because I love the man. Take a look. Let's do something simple. This is gonna be y equals 2 to the power of x, okay? This is x. -3, -2, what's this way? 2 to the power of 1 is, you said this is all you. 2. 2 to the power of 2 is 4. 2 to the power of 3 is, come on, 8. And 2 to the power of 4 is 16. Okay, so what's happening? Every time I go up in an exponent, what am I doing here? I should be multiplying by a 2. What am I doing here? Multiply by 2. And? Okay. So if I go up in an exponent, I'm multiplying by 2. But if you do it in one direction, you should be able to do it in the other. So if I go down by an exponent, what am I doing? Divide by 2. If I go down, what am I doing? Divide by 2. What am I doing? Divide by 2. So if I go down further and I do 2 to the power of 0, what is 2 divided by a 2? And here's my proof. Anything to the power of 0 is 1. Let's go further. Does the pattern change? No. So this should now be 1 divided by 2, right? Let's go further. 2 to the power of -2. What is half divided by the 2? 1/4, which can be rewritten as 1/2 squared. 2 to the power of 3. 1/8, which could be rewritten as 2 to the power of 3. So a negative could technically be replaced or technically be processed as the same exponent, but a reciprocal, 1/2 to the power of 3. So anytime you see that as a negative, you can link those two together. You can automatically assume that if you have an exponent on the bottom, that could be a negative exponent on the top. And vice versa, of course. Yes. And it, if it was written like this, are you talking about the final answer, or are you talking about the? Well, yeah, correct. Take a look. If this is my exponential curve, at any given point, are any of my y values negative? No. So let's pretend this is 10 to the power of x, right? So the logarithm right here would be y is equal to log 10 of x, right? And that x value, of course, the x value itself, the y value, yes, it could be a negative because the x value could be a negative. But here, the y value can't be a negative, and so the x cannot be a negative. Yeah. Okay. All right. I ended up doing all three. Rewrite the following in exponential form. I think you'll be able to handle that. So in summary, a logarithmic function is the inverse of the exponential function. So we were just doing that. Might as well just work that out again. Let's pretend that is 0, 1. And I have an exponential curve going this way. And as a inverse, so let's do y equals b to the power of x. This would be y is equal to log b of x. Okay, and I gave you a couple of definitions on the box where I tried to preserve where the location of x and y would be. So if y is the answer, that answer is plugged into the log, right? If so if y is the answer, if the y is the answer of an exponent, it would be placed inside the logarithmic function. If y was the answer of a logarithmic function, that is the exponent of a exponential function. Okay, and that's pretty much it. That's the first part of our lesson. So we will wait until time runs out and we go for our walk. During that time, if you could try example 3, and if you still have more time, you can either study for your your quest or take a look at some textbook questions. Yes, Hinda. Uh, not times. It's sort of like sine, cosine, and tangent. A log is a function. So you just put a number in there and it will calculate for you. Which are you talking about this portion right here? So all I wanted to show you was, I know, but this is the same XY graph. So notice how the Y value in this case is whatever my answer would be. The Y in this case is what the X was before, right? So it's in the same axes. That's why I wrote this. Maybe it became more confusing to you. The original answer of an exponential function, you will find it being plugged into the logarithmic function. And the answer of a logarithmic function is the exponent of the exponential function. I switched these up without having to like. I'm not sure if that helps. I'm not, I think I confused you. I was just trying to show you where the numbers would be found if you went from an exponential to a logarithmic. I didn't mean to confuse you in that way. Yes. So how about I highlight it? The y value, in other words, the answer of an exponential function will correspond with the number that you plug in here. So if the y value is 1,000, right? So it's like x equals 4, y equals 1,000. In this number, you would plug in 1,000 and you would get a y value of 4. It's going to be switched. Okay. Any other questions? Yes. Mm-hmm. Correct. Yes, exactly. So good question, everyone. If there is no evident log base, by default, it is assumed that it is 10. And also, shameless plug into the sciences, instead of log, if it's ln or ln, it is basically log the base e, Euler's constant. Something that you might see if you go into sciences quite often. And as opposed to log 10, at least in the sciences, we really enjoy using base e. Don't ask why, just wait until your professor explains. Okay, any other questions? Okay, so you got three things. Finish off example 3 and then move on to the textbook or practice some test review questions. Yes, Kinda. Pardon me?